Okay. So, last class we are here that alpha is equal to R inverse small r. So, I can say the small r, you know, the small r is nothing but a small r is equal to R n 1, R n 2 like that, and capital R is nothing but a that matrix, this matrix. So, R is this matrix and small r n is this matrix. Okay. So, this matrix and this matrix. Okay. Now, we have to solve this. How to solve this? Solving is done based on the Levinson and Darwin methods. So, what is these methods? Basically, I have not details describe the methods, but let us go through that. So, basically this equation can be solved to set up optimized predictor coefficient satisfy. If I solve this, basically I am optimize the alpha value will satisfy these two equations. Okay. So, these two equations we have derived. So, if I write down that these two equations in matrix form, the first equation is give this matrix and second equation if I included the minimum prediction error, that means if my estimation is very correct, then it should produce the minimum prediction error. Okay. So, minimum prediction error equation it should satisfy. So, if I put these two equation in a matrix form, it will look like this 1 E n p, because same matrix that this equation to main matrix form. Now, if I see I want to solve this matrix, it is shows that if I use the Levinson recursions, that means the ith order solution can be derived from I minus first order solution. So, suppose I have a p is my level of predict, p is the number of prediction that I want, the order of the predictor is p. So, I can say I can iteratively predict the alpha value and I want that if I iteratively predict it, then at pth order will give me the optimum solution or pth iteration give me the optimum solution. So, in Levinson recursion I said we can say that I can predict the current I value or current this matrix equation current value from the previous or ith order solution. So, what is the I minus 1 order solution? R n I minus 1 alpha I minus 1 is equal to E n I minus 1 if I see this matrix. Okay. So, from here we can derive the solution for R n I alpha I is equal to E n I. This we can derive. Okay. How we derive? That is the details explanation, that matrix I can write this way and then I can append 0 vector at alpha multi, this is the matrix, we can do it. You can see that this right and you can find out this is nothing but a mathematics, nothing else in the mathematics. So, I can say gamma minus I to the power 1 is equal to this, and then I can say this is the triphased matrix, special symmetry, we can reverse the order of the equation, we can reverse it, and then once we revert we can combine in two set of multiplication factor R n, this is minus and this is minus both side. So, it is remain same. Okay. And then we choose I minus 1, so that the vector this k I right side has only a single non-zero entity. So, k I which is the weight vector of the predictor is nothing but a gamma I minus 1 divided by E I minus 1, where it is nothing but a R n I minus j equal to 1 to I minus 1 alpha j I minus 1 R n I minus j divided by E of I minus 1. This is the equation number 1 for autocorrelation method solution k I. Okay. Now, if it is this is k I, then what is the E n I is nothing but a, if I see E n I can write down E n I is nothing but a R 0 minus alpha k R n k I k. So, if I use that value, then E n I becomes E n I minus 1 minus k I gamma I minus 1, which is nothing but a E n I minus 1 minus k I square. Okay. So, ith k I is nothing but a this R n I minus. So, R n I means R n is the autocorrelation coefficient, ith autocorrelation coefficient, minus j into 1 to I minus 1 alpha j I minus 1 R n I minus j divided by E I minus 1. This is the equation number 1. This is the equation number 2. Then I can put that value, and this k I is called partial correlation coefficient, partial correlation coefficient. Okay. Then we can solve for alpha j I and this alpha I k I. This is the fourth equation. Okay. So, final solution for a order P, if my LPC order is P, so alpha j is equal to alpha j P, or I can say K, my alpha j P is the my last set of alpha value or optimal set of alpha value, alpha 1, alpha 2, alpha 3, alpha 4, optimal set of alpha value with a prediction error E n P is equal to E 0, E n 0 energy m equal to 1 to P 1 minus k n square. Okay. So, if I write down these 4 equations, implement these 4 equations in a softwares, then I can calculate that alpha value and I can calculate the prediction error. Okay. So, if we see the next slides, so there is a equation. So, if I say here, if I write down the 4 equation, one is k I is equal to, if I write down the equation, k I is equal to R n I minus j equal to 1 to I minus 1 alpha j I minus 1 R n I minus j divided by E n or E I minus 1. What is E n I? E n I is nothing but a E n I minus 1 into 1 minus k I square. So, this is equation number 1, this is equation number 2. Then I can say alpha j I is equal to alpha j I minus 1 minus k I alpha I minus j I minus 1 and alpha j I is equal to k I. This is the 3, this is the 4 equation. So, now suppose I have a speech segment and I want to find out this value k I, E n I, and ultimately I have to find out this value. So, at the end alpha value is nothing but a alpha j p. The p is the order of the alpha j p, where j is also 1 equal to j p. J varies from 1 to p. So, what I want a set of alpha, alpha 1, alpha 2, alpha 3, alpha 4, alpha p, but those set of alpha value can be extracted in iterative matter alpha 1 1, alpha 1 2, alpha 1 3 to alpha 1 p. So, alpha 1 p is my final answer. Okay. So, using these 4 equation, this I can do. So, how I can do it? I just take that, let us take a simple example. I want to find out the order of the predictor p is equal to 3. Order of the predictor p is equal to 3. So, I is varies from 1 to 3 and j is varies from 1 to 3. Okay. Now, if I see k I, so what is R? I is varies from 1 to p and j is varies from 1 to p. So, if I say I want to find out k 1, if I use this equation and want to find out K1. So, what is K1? K1 is equal to Rn1 minus J is equal to 1 to I minus 1 Rn I minus J. Okay. Now, here I say I is equal to 1. Okay. So, J is equal to 1. So, if it is J is equal to 1, then I 1 minus 1 is 0. So, this will not executed. So, this R1 divided by E n I minus 1 is 0, J minus 1 is 0, E 0. Okay. So, what is E 0? Is the energy which is nothing but a R 0. So, I can say Rn 1 divided by Rn 0. Okay. Now, I can find out K2, okay. K1 I find out, then what is E n I 1 is equal to E n 0 into 1 minus K1 square. So, I get the value of K1 here, I can put the value K1 here and find out E1 n. Then what is alpha J I? If you see alpha J I, here I put J equal to 1, I equal to 1. So, it is alpha 1 0 minus K 1 alpha 0 0. Alpha 0 0 is equal to alpha J I 1 1. Alpha 1 0 alpha minus K 1 0 0. I can get the Q alpha 1 and alpha 1 1, then I can say alpha 1 1 equal to K 1. Okay. So, alpha 1 1 is equal to K 1. Okay. So, this way this is implemented in here. If you see, this is the implementation. Okay. The program is here. So, you can write the program using this 4 equation. Okay. Now, sometime you may find out that is called normalized autocorrelation. So, normalized. So, if you see the autocorrelation, the value of reflection coefficient or K I or alpha I, both are depends on R value, autocorrelation, value of autocorrelation. So, sometime if you find that value of, if it is magnitude is change of the speech signal, then maybe R value will be changed and autocorrelation coefficient may slightly changed. So, what I want normalized autocorrelation, that with respect to R 0, I can normalize that correlation value. So, suppose my correlation value is 1, R 2, R 3. Now, I can normalize R 1 with respect to R 0, because R 0 is the energy of the signal. So, I can say R, instead of R 1, I can use small r 1, which is nothing but R 1 by R 0. R 2, small r 2 is nothing but a R 1 by R 0, R 2 by R 0. Similarly, R 3, small r 3 by R 0. So, those are called normalized. Then if I use this small r to extract the value of K I and E I and alpha I j, then I can say this is normalized autocorrelation. Normalized autocorrelation. So, if I say what is the normalized prediction error? If it is normalized, then prediction error E 0 is equal to 1, because it is R 0 by R 0. So, it is nothing but a m equal to 1 to I 1 minus k m square, I varies from 1 to p. Okay. So, this is a normalized autocorrelation. So, this is the program, you can implement it and find out whether it is happen or not. Then that is the task I have given. The consider a sample p is equal to second order p is equal to find the solution. So, I can give you, let us x n is equal to, I give you not speech signal, let us 1, 2, 5, minus 1, 2 like that, and then I told you that for p is equal to 2, find out that alpha 1 and alpha 2 and find out the autocorrelation error E. Okay. So, you can find out k 1, k 2. So, I can say E is equal to nothing but E 0 into 1 minus k I square, where I varies from, I can say 1 to m square, m equal to 1 to order 2. So, it is nothing but E 0 into 1 minus k 1 square into 1 minus k 2 square. I can find out, and I can find out alpha 1, alpha 2 using this equation in handmade without programming. So, if p value are very less, without programming I can find out that alpha 2. So, those kind of questions can we expect in that examination paper, or I can write a program and run a real speech signal and find out the that alpha value and E value for autocorrelation function using the autocorrelation coefficient. Okay. So, those are the autocorrelation solution. Okay. Now, how do you define the order of the p? So, I say prediction order. So, how which factor the p is dependent? Prediction order. I have to take a signal which is 8 kilohertz sampling rate, I have to take a signal which is 16 kilohertz sample, I have to take a signal which is 32 kilohertz sample. So, different sampling rate I can sample the speech signal. Now, what kind of order I should use to get the correct coefficient value? If it is true that if I increase the order, your error will be less. So, I cannot take infinite order. So, what kind of order is optimum? So, in what basis I can decide the order? So, if you see that in tube model for formant, every formant are separated by 1 kilohertz. 1 kilohertz signal. So, if you see, if you remember in the first class, the first tube model, uniform tube model, if it is tube length is 17.5 centimeter, first formant is 500 hertz, next formant is 1.5 kilohertz. So, they are separated by 100 hertz or 1000 hertz, that means 1 kilohertz. So, I can say that if it is my Fs is my sampling frequency. Okay. So, what is the baseband frequency? Fs by 2. How many complex pole is required to realize one formant? 2. Complex conjugate pole is required to realize one formant. So, it is 2. So, Fs by 2 into 2 pole, how many? Every 1000 hertz signal. So, I can say Fs by 2 into 2 by 1000, 2 cancel. So, I can say Fs by 1000 number of pole, number of complex conjugate pole, complex pole, not conjugate, then it is will be half. So, complex pole. So, if it is 8 kilohertz, then 8 k divided by 1000. So, I can say 8. If it is 16 kilohertz, then 16 k divided by 1000, 16. If it is 32 kilohertz, 32 k divided by 1000. So, it is 32. So, those are for formant, that means those are for tube only. Next is there is a glottist and there is a radiation loss. For glottist 2 to 2 poles and for radiation loss 2 to 4 pole. So, if I say radiation 2 pole and glottist 2 pole, so 2 plus 2 is equal to 4 pole, 4 plus 8, 12 pole if my signal is sampled at 8 kilohertz. If my signal is sampled at 16 kilohertz, then I can say 16 plus 4, 20. 16 plus 20 or 21 or 22 I can say, 16 plus 6 also, if the glottist, if the radiation loss is used by 4 pole. Okay. So, order of that LPC analysis it is not arbitrary, it depends on the sampling frequency, it depends on the sampling frequency. So, based on the sampling frequency, I can take the order and find out the LPC analysis. Okay. Now, there is another question is there, how LPC analysis, then if I have a speech signal, I extract that filter. LPC analysis give me the alpha 1, alpha 2, alpha 3 value. Those actually characterize the vocal tract. Okay. Now, forget about this part, I will come later on. Then, if those coefficients are represent the you can say the pole position. Okay. So, format those are the represent the actually pole position. So, I can say if I take the frequency transform of those coefficients, I should get that LPC spectrum which will give me the resonant frequency. Have you understand or not? So, if I say Fs by 2 number of pole, I said okay, now those coefficients are represent the pole position of the speech signal. Now, if I take the spectrum or the frequency analysis of this LPC coefficient, this should give the LPC spectra, they should represent the peak at formant frequency. Okay. Now, if order of the analysis is reduced, then this should be, so suppose I require let us 14 order, I make it 12 order. So, some of the format will combine together and give me some broad kind of structures. So, if we see in this picture, if my LPC order is increased, it more or less copy the actual, the blue color is the actual spectrum, and if you see the red color where LPC analysis is 10. So, there is a lot of formats are there. So, I can see that it is roughly estimate that spectral envelope. If I increase the LPC order, the number of variation is increases. So, it accurately increase the, it accurately copy the spectrum envelope. Okay. So, depending on my requirement, if I want the smooth spectrum, I do not want this lot of variation, then I can use LPC order, reduce the LPC order. If I want that I want to exactly copy the spectrum, then I can increase the LPC order. Okay. So, using this I can also draw the spectrogram also. This is the real life example of LPC spectrum. So, if you see how many formats are there, 1, 2, 3, 4, 5, 6, 7. Now, if I say what is the possible order of the LPC analysis? What is the possible order of LPC analysis? So, I can say there is a 7 format. So, I can say 7 into 2, each format requires 2 complex pole. So, it is nothing but a 14 order LPC analysis. Okay. So, this can be explained, this is called LPC spectrum, and then there is a LPC spectrogram, this is the frequency analysis equation. You can go through that slides. I have not details described this frequency analysis equation, and this is the LPC spectrogram, because here if you see the formats are much more clear. Okay. This is done. How it is plotted? You suppose you have a speech signal, you take a window, find out the LPC coefficient, take the spectrogram of the LPC spectrum of the, draw the magnitude spectrum of the LPC coefficient. Then for that time plot this in this frequency scale, again shift it and plot it, and that way you get the LPC spectrogram. Okay. So, this is LPC spectrogram. Now, okay, format, suppose that this I will discuss later on, and also I have discussed in that during the tube analysis, that formant position r e to the power j theta. So, if frequency of the formant is given by Fs by 2 pi into theta. So, if I say every complex conjugate pole indicate one formant. If it is close to unit circle, this is called formant frequency, it contributes to the formant frequency because energy will be very high. So, if I say complex conjugate pole, so suppose this is my unit circle and if there is a formant, there is a pole, angle is theta. So, there will be the system is real. So, there will be a complex conjugate pole minus theta here and this is R. So, R, which if it is close to unit circle, the bandwidth R will be increased and bandwidth will be increased. If it is close to 0, the bandwidth will be 0. So, if we see the formant frequency is determined by this angle theta and the formant bandwidth is determined by R, which is already explained in tube modeling. So, if Fs is my sampling frequency, okay. So, what is the normalized frequency of the digital signal is 2 pi is equal to Fs. Okay. So, what is the value of the theta? Theta maximum value is 2 pi and which is equal to Fs. So, if the theta is let us 30 degree or this radian, if it is radian, let us it is x radian, then I can say Fs by 2 pi into x is the radian is the frequency. If it is hertz, then I can convert Fs is in hertz. So, I can say Fs by 2 pi into x hertz is my formant frequency. So, suppose I have a pole, I do not know whether the example is here or not, no example is not there. So, suppose the theta is equal to let us 30 degree or let us pi by 3. So, what is the formant frequency? So, let us Fs is equal to 16 kilohertz. So, if it is 16 kilohertz, then Fs by 2 pi into pi by 3. So, Fs by 6 is nothing but a 16 k divided by 6, it is 1 kilohertz by formant frequency. And formant bandwidth is nothing but a Fs by pi into log of this is z r, log of r you know that, log of r, what is r? R is nothing but a absolute value. So, if it is complex pole is a plus jb, then I can say root over of a square plus b square or mod of, if it is pole is zk, mod of zk give me the r. So, I can say pi by Fs, Fs by pi into minus log of abs zk or mod of zk. Okay. So, I can find if the r value I know, if I know the sampling frequency, if I know pi I know. So, I can go the I get the formant bandwidth or vice versa. If I know the formant bandwidth, I can find out the value of r. If I know the formant frequency, I can find out the value of theta, then I can derive the transfer function of that things, because z is nothing but a r into e to the power j theta, or you can use that r theta equation in tube model. Okay. So, both way, if I know the formant bandwidth and formant frequency, I can derive the transfer function, linear LTI transfer functions, or if I know the if I know that the pole position or pole value or theta and r, I can derive the formant frequency and bandwidth. Okay. So, this is autocorrelation method I have described and all other things I have described. Then there is a other methods also, that if you see that there is a covariance methods for linear prediction, covariance methods for linear prediction. So, covariance methods is also another methods. Instead of autocorrelation, I can find out the covariance method to detect the to find out the LPC coefficient. So, what we want? We want the same things, same solution of that matrix, solution of this matrix. Okay. This we have already derived. Now, the difference is that in this matrix, that I have not taken the outside the window signal is 0. If I take it, then problem will come. So, what we will take? The key difference control method is that limit of summation include the term before m equal to 0. So, if the order is p, instead of 0, I have to consider the previous sample also, and here also I previous sample also I have to consider. So, if the order is p, p number of previous sample I have to consider. So, tapering of the window does not matter here, the window does not matter here, whatever window function I can use, but I should say that p number of previous sample is required in this analysis. Okay. Then same simple things, I have to solve this matrix equation. So, phi, you can say this psi into alpha is equal to let us this one. Okay. Then I can say alpha is equal to phi inverse, or I can write this is not phi. Okay. I have to solve this. Now, this can be solved called Chomsky decomposition methods, which is that let us phi is equal to matrix A D A transpose, and phi into alpha is equal to let us this one. Okay. If phi is this matrix, where A is called lower triangular matrix and first one in the main diagonal, and D is the diagonal matrix, and A transpose is the upper triangular matrix. So, I can say, so instead of let us solve for p equal to 4, order is equal to 4. So, I can get phi equation is phi 1 1, phi 1 2, phi 1 3, phi 1 4, phi 2 1, phi 2 2, phi 2 3, phi 2 4, phi 3 1, phi 3 2, phi 3 3, phi 3 4, phi let us 4 1, phi 4 2, phi 4 3, phi 4 4. This matrix let us equal to a lower triangular matrix, that is diagonal element is 1. So, 1, then it is A 2 1, A 2 3 1, A 4 1. Okay. Then I can say put 1, I can say A 3 2, A 4 2. Okay. Then I can put 1, I can say A 4 3, then I put in 1 here. Rest are 0 0 0 0 0 0. This into let us diagonal element D 1, D 2, D 3, D 4, 0 0 0 0 0 0 0 0 0 0 0 0. Okay. So, diagonal element and A transpose, if it is lower triangular, is the transpose is upper triangular matrix. So, this is this. Okay. Now, if I solve this, then I can get solve this matrix. If I solve this, D 1 is nothing but a phi 1 1. Okay. Similarly, A 2 1 is nothing but a phi 2 1 divided by D 1. A 3 1, if you see that A 3 1, you do it, phi 3 1 by D 1, A 4 1, phi 4 1 by D 1. Now, if I solve for D 2, if I solve for D 2, it will come phi 2 2, this will be phi, there is some typing mistake. So, phi 2 2 minus A 2 1 square into D 1, this will be phi. Okay. All are phi, this is phi. So, I can write down the program, I can generalize this D equation and generalize the A equation and write down that program. So, I can find out the D and A value. Okay. Now, once I get the D and A value, let us I find out D and A value in terms of D and A value I get in terms of other D and A value. Okay. So, D 1 in terms of phi value I get it. Now, if I see A D A transpose alpha is equal to let us this one. is instead of A, this one I write A into Y. So, I can say D A transpose alpha, D A transpose alpha is equal to let us Y matrix. So, I can write down this one again A 1, Y 1 and this one, and then again I solve and generalize this one for any order. This is the generalization. I can write down this matrix, I get Y value. Once I get that Y value, so this is D A transpose alpha is equal to Y. So, I can say A transpose alpha is equal to D inverse Y. Okay. So, D inverse I can easily calculate. Then I can say alpha A transpose alpha is equal to D inverse Y. So, I put that A value, I put the alpha value matrix, D transpose and Y. Then I can get that alpha 4, alpha 3, alpha 2, alpha 1. So, it is reverse order we are getting. We can write down the equation, generalized program. So, I can get using this matrix decomposition technique, I also can calculate the alpha value if I know the phi value, because phi value is nothing but a phi ik is nothing but a this one within the window. Only difference is that in matrix, this covariance matrix, at m equal to 0, this side the signal is not 0. I require the p number of previous sample, okay, because this restrict me. So, this is called autocorrelation methods. Okay. Then there is a other techniques also, that is called lattice methods, that we will discuss in the next class. Let us discuss in one things which is there, which is important, which is called gain. So, what I am saying, in LPC analysis we can say, if I apply the, if I know the alpha value or k value, I can design this filter, and if I know the voice signal is nothing but a impulse. So, I generate the impulse based on that f0 value of the voice signal and multiply the gain let us g, and then if I can pass through this filter, I can generate the speech signal. So, if it is LPC decoder, let us simple LPC encoder and decoder. So, if I want to transmit this signal from this point to this point using simple LPC encoding and decoding, what I want? I want to send that f0 value, g value, alpha value or ki value in the receiver end, and from f0 value, g value and alpha value I can generate the speech signal. So, f0 is extracted based on the, if I get the speech signal, I can extract that f0 value. So, next I have to calculate, I can use ki value, I can extract the ki value using the autocorrelation technique or covariance technique. Then next I have to know the g value. What is the g value? Gain value. So, how do you calculate the g? If you see, I can calculate easily, I can calculate the computational model gain of the signal. If you see, Hz is nothing but a g by 1 minus k equal to 1 to p alpha k z to the power minus k. This is the LPC equation. Okay. Or I can say, in time domain, if I multiply it this side, Hz minus Hz into k equal to 1 to p alpha k z to the power minus k is equal to g. So, I can say Hz is equal to Hz into k equal to 1 to p alpha k z to the power minus k plus g. Okay. So, if it is Hz, it is nothing but a, I can time domain Hm is nothing but a k equal to 1 to p h alpha k h of m minus k z k sample delay plus g. If I say my input of the system is a delta function, okay. So, I can say the g is nothing but a gain with a delta function. At m equal to 0, only g exists, is the gain. Okay. Now, if I multiply both sides h m multiply by h m, so I can say k equal to 1 to p alpha k h of m minus k into h m plus g del m into h m. Okay or not? Okay. So, if it is that, so what is h or m, let us m minus I multiply, m minus I, multiply both sides by m minus I. Okay. Now, at I equal to 0, h m into h m minus I is nothing but a h m multiply by h m. Okay. K equal to 1 to p alpha k, okay, alpha k into m equal to minus infinity to infinity h m minus I have taken minus infinity to infinity h of m minus k into h m. Forget about this part, alpha k into h of m minus k into h m plus g of delta m into h m. Okay. Now, h of m into h of m is nothing but a autocorrelation R 0 minus k equal to 1 to p alpha k, this is nothing but a R k, plus this is g, and what is del m and h m at m equal to 0, del m is only exist at m equal to 0. So, I can say this h m is nothing but a k equal to 1 to p alpha k h m minus k into plus g into del m. Now, at m equal to 0, because del m is only exist at m equal to 0. So, here at m equal to 0, I can say k equal to 1, this is nothing but a g. So, I can say g into g. So, g square. So, I can say g square is nothing but a R 0 minus k equal to 1 to p alpha k r k, k equal to 1 to p alpha k r k. If know the alpha value, if I know the r k value, if I know the R 0 value, I can calculate g square. Once I get the g square, I can calculate g value. Is clear or not? So, whatever the speech segment I get, once I know the speech segment, I can calculate the alpha value, I can calculate the r value, R 0 and r k, all r k value. If the order of the predictor is p, then I can calculate r 1, r 2, r 3, r p, and I can calculate alpha 1, alpha 2, alpha 3, alpha p, then I calculate the g. Once I get the g square, g is equal to nothing but a root over of that things. So, model gain I can easily compute using this theory. Okay? Okay. So, next class we will discuss about that, which is very important, lattice modeling for LPC extraction and also LPC parameters, that extraction, also implementation of pole 0 filter, all those kind of things we will discuss. So, LPC synthesizer, because that is very important. How do we synthesize the speech signal at decoder once I know the k value and alpha value? Okay.